This is Grant Geiger, and I'm doing the Wagon Bot Demo. So nowadays, robots are doing a lot of the heavy lifting in the world. On the left is an example of an Amazon warehouse robot. Amazon alone has over 200,000 of these warehouse robots that make sure that you receive your packages on time. On the right is a small food delivery robot that DoorDash is trying to implement in big cities. As robotics become more advanced, these types of delivery robots will become more and more common. My robot is the Wagon robot. The Wagon robot is a more robust version of the food delivery robot, and it can go on any terrain. The inspiration of this robot is for my dad, because he wanted a robot that was completely autonomous and could bring in wood for him. So I grew up in Wisconsin, and at times the trail is icy to the wood pile and there's snow on the ground. So this robot has to be able to go on all different types of terrains and be able to survive the cold winters. The picture on the right shows the field of vision of all the sensors on the robot. The two hemispheres are two LiDAR detectors. Normally you'd only use one LiDAR detector that is placed over the center of the robot. But in this case, the center needs to be accessible, so I had to make a sacrifice and use two LiDAR detectors. To cover the blind spot of these detectors, I use 3 ultrasonic sensors on each side, and they cover almost all blind spots of the wagon. So this is a short video showing an exploded view of my wagon. So the Wagon Bot has 2 different batteries, and then you've got 4 motors, and then your 10-inch wheels. You got the 2 LiDAR sensors and the 6 different ultrasonic sensors, and then you got the main frame. In total, this wagon would be able to haul 80 pounds of payload over rough terrain, and the batteries would last at least 3 hours. So now we got to put it back in. And all these parts are able to be bought online and are the exact dimension that was provided by the product owners. So if I wanted to, and if I had an extra $1,400 lying around, I could make this part and make the whole model. So I wasn't happy with just making the model itself. I wanted to simulate it in Gazebo. So on the left is a collision assembly for Gazebo that I made, and it accurately represents all the dimensions of my robot. The collision model has to be simple because Gazebo can't handle too much, and this simple model is supposed to be able to work in Gazebo. Now, on the right shows SLAM, which is the process that I wanted to use to allow the model to traverse throughout the environment. So things didn't happen the way that were planned. I was able to get the collision assembly into Gazebo, but then when I tried clicking on it, nothing would happen, and you could technically place it down, but it would end up just crashing the system later. So this error was caused by a converter that Ross has that it was supposed to convert a URDF file into an SDF file, which is what Gazebo needs, but in my version of Ross, the converter just struggles, and in this case we lost 2 wheels and 2 axles and you can't see anything. So it's not going to work, and I was very disappointed, but I wasn't giving up just yet. So instead, I used a turtle bot to simulate what I would do with my actual robot. So I launched Gazebo, and I launched a specific house setting to understand how to get this turtle bot through the doors. So in this process, I'm just setting up SLAM, and I'm got to set up the 2D pose estimate so that the robot knows where it is in the environment. This estimate wasn't that great, so I did it again. And now, to allow the robot to have a better understanding of where it is, I have to make it move around the environment so that the LiDAR detector can sense where objects are and get a proper bearing on where it is in the environment. The green dots you can see around the little robot are possible positions that the robot might be in according to the SLAM system. SLAM is a common way people use LiDAR detectors to create path planning and have the robot itself figure out where to go. So now that I got the position basically down, there's still some error in it. I'm going to have a navigation goal set. So now the robot will follow the path, and you can see in Gazebo, this robot is actually going exactly where RViz thinks it is. So the SLAM application is working well, and I was very curious. I would love to see this with my actual robot to understand if it can actually maneuver in these tight spaces. So my robot definitely can fit through all the doors. It's only 23 inches, and most doors are 32 inches wide. But it's a little over 3 feet long, so it might have a hard time navigating through the small spaces like that room. And that is my slides. So if I were to improve this, I would love to have had my robot in the Gazebo simulation, but I'm just not skilled enough in coding to actually make that happen, because I would have to change the URDF codes into SDF code. But another challenge that I would find interesting with that is I have to get the sensors working too. So I would have to apply the sensors and make sure that all the data and the ranges are coming in correctly. Thank you so much, and that was my Wagon Bot.